Welcome to Data Science with Scala, produced in conjunction with the Data Science Retreat. This course is intended to teach data scientists how to use Scala to perform analytics using the Apache Spark ecosystem. My name is Priya and I will be your guide for this course. My background is in probability and statistics, and I completed my PhD at Columbia University and the Australian National University. Currently, I'm using the Spark ecosystem with Scala for customer relationship management of mobile commerce products. This is where I've observed the efficiencies of using Scala with Spark. In this first lesson, we will discuss vectors and labelled points. After completing this lesson, you should be able to understand local vectors and labelled points, create dense and sparse vectors, and create labelled points. MLib has its own vectors with linear algebra operations provided by Breeze, a numerical processing library for Scala, and JBLUS, a fast linear algebra library for Java. Now, by default, Scala uses its immutable vector from scala.collection. So you have to import MLlib's vectors from org.apache.spark.mllib.linalg in order to use MLlib's implementation. Just like a regular Scala vector, indices in MLlib's vectors also start with a 0. But in MLlib's implementation, all the values in a vector must be doubles. MLlib's vectors are local and stored on a single machine, and they can be either dense or sparse. As a point of reference, a vector is a point in some multidimensional space where the dimension is the number of elements in a vector. It is a non-fixed length sequence. A matrix is a two-dimensional array, n by m, a collection of vectors, all of the same length, and always forms a rectangular structure. From now on, unless specified otherwise, every reference to vector must be understood as a reference to the MLlib's implementation. Let's start with a dense representation of a vector. It is the obvious and straightforward implementation of a vector. A dense vector can be easily created from an array of doubles, and that is how it is represented internally. Here's an example of creating a dense vector. After importing both vector and vectors, I can create a dense vector by calling vectors.dense and providing all double values that I want to be in this vector. res0 shows me I've created the right type of vector, and that it indeed contains all values I passed as parameters. The sparse vector type, on the other hand, is backed by two arrays, one integer array representing the indices of all non-zero entries, and one double array containing the corresponding values of those entries. It is a binary search implementation of a vector. A sparse vector can be created in two different ways. You can specify two separate arrays, one for indices and another for the corresponding values. Or you can specify its non-zero entries as a sequence of tuples, where the first element is the index and the second element is the value itself. Earlier we created a dense vector. Here we show how to create an equivalent sparse vector by using vectors.sparse, which we can do in two different ways. In both examples, we must begin by specifying the total size of the vector. In this case, I'm creating a vector with 3 elements. Then in the first example, I provide an integer array containing the indices of all non-zero entries. In this case, I'm creating a vector with its first and last elements different from 0. Remember, the indices are 0-based, so the indices are 0 and 2. And the third argument to vectors.sparse is a double array containing the actual values, in this case 44 and 55. The resulting sparse vector is shown in res1. Alternatively, I can also create the same sparse vector by providing a sequence of all its non-zero entries as tuples. In this case, for index 0, I have a value of 44, and for index 2, I have a value of 55. Now, as expected, res2 is exactly the same as res1. Now let's talk about labelled points. A labelled point is the association of a vector, either dense or sparse, with a corresponding label or response. Labelled points are designed for use in supervised learning algorithms. If you think of a vector as a representation of features, a labelled point is a natural extension to it, allowing the inclusion of the corresponding label or response. So, for example, if we had a set of variables, maybe pixel information that could describe whether a photograph was a cat or a dog, the labelled points will label each photo in the dataset as a cat or a dog. Now, unsupervised learning methods like principal components analysis don't contain labels or responses. Instead, they rely on algorithms to partition the data. So in the case of image recognition, maybe we have pixel data that will end up clustering based on image type, where image type might be dogs or cats. It is worth noticing that the labels are also stored as doubles, so they can be used in both regression and classification algorithms. For binary classification problems, the labels must be either 0 or 1, representing respectively negative and positive responses. And for multi-class classification problems, labels must be class indices starting from 0. Now let's create some labelled points. First, I create a labelled point associating the value 1, which could be a positive response for a binary classification problem, like a flip of the coin, with its corresponding features, that is, a dense vector with values 44, 0, and 55. Then I create another labelled point, associating a 0 response to a sparse vector of size 3, containing the value 44 in its first position and the value 55 in its last position, just like before. Having completed this lesson, we should now be able to understand local vectors and labelled points, create dense and sparse vectors, and create labelled points.